Hello, one and all. Bienvenue à tous. If you're tuning in live, thanks for making the time for us in your busy day. If you're watching this on YouTube, thanks for stopping by. Whichever way you're watching, welcome to Postmedia's third season of Driving into the Future. Today, the subject we're tackling will be, is the infrastructure the last roadblock to EV domination? I'm David Booth, and I'm the senior writer for Driving.ca. Canada, as we all know, is moving rapidly to convert our automotive fleet to electrification. By 2030, the federal government estimates that 60% of all new car sales will be electrified. And by 2035, all cars sold in Canada should be battery powered. Transport Canada even knows how many electric cars will be on the road on a year-to-year basis. By 2040, for instance, the government thinks there will be 20 million plug-ins on the road, representing almost 2/3 of the passenger cars driven by Canadians. What would seem less concrete is the plan for the charging infrastructure for all these vehicles. Simply put, the plan to sell electric vehicles would seem a lot more robust than the directive to service them. So today, our panel of experts will try to answer those tough questions. How many recharging stations and ports do we have? How many will we need going forward? Is our electric grid up to the task? And again, moving forward, how much green energy will we need to serve our future net zero aspirations? To help us answer all these questions and more, we're joined today by Rami Azar, PhD, VP and Market Lead of Power Grids for SNC-Lavalin, Talis Blelac, PhD, Managing Director of Aspire, Claudio Canizares, PhD, PEng, Professor at University of Waterloo, and Brian Kingston, President and CEO of the Canadian Vehicle Manufacturers Association. Welcome, gentlemen, and thank you so much for joining us today. Before we start the proceedings, let me welcome all our viewers and inform them we will be trying to answer some of your questions at the end of this discussion. So, gentlemen, we're definitely at a crossroads in the auto industry now. Governments on all levels are supporting EV sales like never before. The federal government has outlined specific plans on how many electric vehicles will be sold over the coming decade, and legacy automakers, reluctant to embrace battery power, have jumped in with ambitious plans to roll out a plethora of new plugins. The EV revolution has well and truly started. But if we're going to go all electric, we're going to need a radical upgrade to our recharging infrastructure. So let's try to figure out what that future looks like. Rami, jumping right into it, your company builds and engineers much of the infrastructure that feeds Canada's electric grid. You have also produced extensive research on how much power production we're going to need forward to reduce all our greenhouse gas emissions. And by all, I mean more than just the automotive industry, though it is a large part of the equation. So how much electricity does Canada produce today? More importantly, how much will we need in the future to keep all our net zero promises?
Okay. Thanks, David, and thank you for having me. So yes, indeed, in my role at SNC-Lavalin, I've worked on some large-scale transmission and distribution projects. We do it in Canada and internationally. So everyone thinks always, am I generating clean power? You know, whether it's hydro, wind, solar, nuclear. People forget that once you produce the power, you also have to transport it to the point of consumption. And this is the transmission and distribution. So all of this generation, transmission, and distribution are the daily bread of my Power Grids division here at SNC. So if we talk about greenhouse gas emissions particularly, first of all, the government has made several separate but related commitments. Amongst them, they committed to a 45% reduction in greenhouse gas levels by 2030, a net zero power grid by 2035, and all of this is en route to total net zero for the country by 2050. So to give you an idea what the scale of these reductions represent, if we just want to meet the 2030 target as a start, and we look at reductions across all sectors, including transportation, just for transportation, it would be necessary to replace every combustion engine car, light truck, and van in BC, Ontario, and Quebec. All of this in the next 8 years. Okay, so it's a pretty big undertaking. This is all part of a decarbonization plan. So how do we do it? Well, there is a consensus that Canada has very abundant natural resources. So in our case, the most promising pathway to net zero is electrifying our sectors of activity as much as possible. According to a number of Canadian think tanks who have looked at the problem, as well as our own predictions at SNC, we looked at a model for 2050, and we see that by then we expect the electrical load will triple as we move towards net zero. Okay, so a lot of it is related to transportation. Some of it is related to converting heating from gas to electric. Some of it is industrial, etc. But it's all going to happen at the same time. And to put things in perspective, if we were going to meet this load increase using one type of generation, it would be equivalent to building 115 copies of BC Hydro's Site C hydropower facility. If we were to do it with nuclear, it would be 19 times Ontario's 8-reactor Bruce Power facility. And if it was going to be wind turbines, it would be 20,000 large turbines, okay? Now, as if all this wasn't enough, this is the generation to meet the new load. You still have to keep in mind that, number one, we have to retire and replace the existing coal generation. Then we have to replace the current generation that will be retired between now and 2050. Then we're going to add the generation that we would have needed if there was no net zero, no electrification whatsoever. And then after all that's done, then you start adding the generation we just talked about required for net zero. And while all this is happening, obviously, you got to build the transmission and distribution infrastructure that's going to support all of this new generation. So it's a huge challenge. I don't want to sound like I'm the merchant of gloom or anything. This is why engineers are there. We're there to solve problems. And we have to remember that during the 70s and the 80s especially, Canada actually came close to achieving these high energy build rates. And countries like India and China are actually achieving them today. In the 80s, we built the great hydro dams over in James Bay. We built the largest nuclear power plant in Bruce Power, which, by the way, is an all-Canadian solution, right? The CANDU reactors are manufactured by SNC. So all this to say that there's the expertise in Canada, there's the know-how to build all these things. We need to move at a much quicker pace than we ever have before. We're going to have to keep this historic pace nonstop until 2050. And finally, I just want to emphasize one other thing. So in doing this, it's a big challenge, but in doing this, we're going to refresh our energy mix, and we're going to do it with a net zero focus. And what that does, it brings us energy security for the generations to come. Especially now, all countries consider this a big priority, and especially our friends in Europe. And when we talk about expanding those non-emitting technologies like hydro and nuclear, it's also supply chains that are all within Canada. So it's very important in terms of energy independence on top of everything else.
Okay, thanks very much, Rami. That's wow, very comprehensive. I don't think gloomy. I think what you said is we've got a really tough task ahead of us. It won't be easy, but it is doable. So thank you very much. Claudio, before we can deep dive into a need for a future charging infrastructure, specifically for EVs, it would help to understand what we're talking about. Could you walk us through the types of chargers? What's a level 1 charger and what's it used for? Ditto for level 2 and DC fast chargers. How fast do they charge an electric vehicle, and roughly how much do they cost?
Sure. Thank you, David, for having me. A pleasure being here, being part of this important panel. If I may have my slide, my first slide discussing these levels, because it gives you a graphic view of exactly what you are asking. So we have 3 levels of charging. Level 1, which is basically your normal outlet, 120 volts, 15 amps, so something that you just plug in the wall and plug your vehicle. It's about 2 kilowatts, and it basically, it will cost you about $100, $180, $200 plus taxes. So I just actually, when I got my vehicle, I bought it and bought one of these chargers. So easy to acquire, no major issues, and it works for me in terms of, I have a Hyundai Kona electric, and it basically allows me to charge for my needs overnight, the commute that I have with 140 kilometers. Then there's level 2. Now we're getting into a more complicated problem, because now you have 240 volts, 32 amps. So we're talking about between 6 and 8 kilowatts. So that's a significant load in the house. In fact, the big load in my house and more houses in Ontario is about North America in general, 6 to 8 kilowatts. So it's a significant load. So now you're talking about a special outlet, something that you need to install, and it requires a lot more commitment and particularly installation part. The level 2 itself is about $360. I just also got it for myself. Taxes, something around $400 plus the installation cost, if depending on how you install it. And then you have level 3, which is that's when we're talking about a more significant investment. It's about, it varies a lot. I mean, it's a whole range of them. It goes from 150 to 1,000 volts DC. You're talking about 125 to 500 amps. So these are significant loads. So now between 19 and 500 kilowatts. So that could be a very significant load in a grid. And the costs are very significant. We're talking about thousands of dollars. For example, I was just looking at a 100 kilowatt level 3 charger. It was about just the charger about $20,000. Ourselves, we're purchasing one for a facility we're developing. Install this is going to cost us about $70,000 installed. So these are quite significant investments, right? And quite significant loads when you're talking about level 3. Level 1, obviously, is very easy manageable. And level 2, well, requires some investment, some changes that will have an impact on the grid at the level at the distribution level, the transformer level, low voltage grids.
Thanks very much. Brian, Claudio just described in the last with the fast charging stations, the public infrastructure we're discussing today. So I'm looking for you for perspective on our current readiness for electric vehicles. And again, we're talking non-residential chargers. Is there a place for level 1 chargers in public space? And what's the best use of faster level 2 and DCFC charging units? More importantly, how many of these public charging units, pumps for those still thinking of fossil fuels, are there in Canada right now, and where are they deployed?
Great. Well, first, thanks for having me. Great to be here and a great discussion. So just to answer your first question on EV readiness, in short, no, we are not ready. And we have a long way to go to prepare for the onslaught of electric vehicles that are coming into the market. If you look at E&Y has an EV readiness index, Canada's fallen from 8th to 13th place for last year, and that puts us second last. And that's a ranking of top automotive markets around the world. And really the reason is because we have a charging infrastructure challenge and a consumer incentive challenge. So on the EV readiness front, we have a lot of work to do. When it comes to the types of chargers that we're going to need, a couple of things here. Automakers are making major investments, as you outlined. If you look at Ford, General Motors, and Stellantis, over $100 billion into electrification to significantly ramp up EV production. And what they're doing is bringing to market EVs in every segment, but in particular, you're seeing EVs in segments that Americans, North Americans, and Canadians love, which is 80% of sales are in the SUV and pickup truck segment in North America. We love larger vehicles that have a lot of utility. And so you're seeing electrified versions of those vehicles, pickup trucks, SUVs coming into the market. And to deliver the range that consumers demand and the performance, that means a larger battery. So to your question around what type of charging infrastructure is needed in public places, as the technology develops and the batteries become bigger, there's going to be significant demand from consumers for fast charging when they're taking road trips so that those batteries can be charged enough to get them on their way quickly. There will be a role in some instances for level 1, but that's mostly for a plug-in hybrid. I'm driving a PHEV right now, and level 1's fine. I plug it in at my house. I can get a full charge overnight. in a public place, you could get a full charge in 8 to 12 hours, depending on the battery size. So there will be a role for it, but I think given the models that you're seeing coming into the market, we're really going to need more level 2 and in particular level 3 fast charging to give those vehicles the top up that they need and to do it quickly, because at the end of the day, convenience is key here to help consumers make the switch. In terms of where we're at on charging right now and how many units we have, there's 19,000. That's the most recent estimate from NRCan, which has operates a database of public charging ports. And deployment is largely, it's BC and Quebec, where they've been real leaders in this space in terms of charging infrastructure. So about 3,700 in BC, 6,900 in Quebec, and then 6,200 charging ports in Ontario. And if you could just put up the chart that I wanted to speak to here. This is from the federal government's most recent assessment of charging infrastructure needs in Canada, and it gives you a good look at where we're at and where we need to go. So the federal government's committed to funding 84,500 public chargers, and as of September, there were 2,500 operational publicly funded charging ports in Canada. And if you look at the black bar there, that's the assessment of what's going to be required. And the red bar shows you what the government's current plan is. So we've got a huge gap there. And as you can see with the line, that's the growing ZEV fleet as projected by Transport Canada. So the assumption is that the public sector or the private sector is going to fill that gap. That is a significant gap. And as I'll get into later, I would argue the gap is even larger. So we've got a big challenge ahead of us. It is possible to overcome this, but we have to get moving and we have to be more ambitious with our build out right now.
Wow, thank you very much, Brian. And what a great introduction to talking with Talis. Talis, thanks for joining us all the way from California. Almost all of the talk surrounding our public charging infrastructure is dominated by discussions of charging points and fast chargers. For most of us, plugging in is the only way we've heard of to keep our electric vehicles fueled. But there is another way, isn't there? Your research center, Aspire, is working on something called inductive roadway charging. Now, a few of us have heard of the possibility we could eventually use wireless charging pads built into our driveways so we don't physically plug in. But you're talking about a technology far more advanced than that, aren't you? Why don't you walk us through it?
Thank you, David. I appreciate the opportunity to contribute here on the panel this morning. For those of you who haven't heard of inductive charging, it's pretty simple. Just as I can take a wireless charger and put my cell phone on it and charge, we can do the same thing for vehicles. So it's a lot higher power, and we can separate it so it doesn't have to be sitting directly on top of it. So you can get, say, 10 inches of clearance from the bottom of the roadway to where it may be on a larger vehicle versus a passenger car. But if you think about pulling into a parking spot, we can do stationary wireless charging. So instead of having to get out, especially when it's really cold or something else, and plug in your vehicle, you can drive over the top of it and you can charge. And for anybody that's mobility challenged, this means I don't have to figure out how do I get out, get my wheelchair, plug it in. There's a lot of benefits that come in. But we can take it a lot further than that. We can actually charge a semi-truck doing 70 miles an hour down an interstate highway with this technology as well. So it opens up a lot of different possibilities. When you look across the world, people are trying different things. In Germany, Siemens has built a highway where they have a catenary system where you have a connection of wires up above, like you'd see in old-time buses or trains. And that works for big rigs, but you can't share that between passenger cars and delivery vans and trucks. So by actually embedding coils in the roadway, putting a receiver coil on your car, we can actually charge vehicles when they're going. And using these electrified roadways can drop the cost of transportation for all of us. And we'll talk about more of that later.
Thanks very much. I mean, that sounds really exciting. I'm really interested to hear the cost analysis. Rami, you mentioned that all those alternatives that would be needed to generate the clean electricity that we'll need for a net zero 2050 was about 19 nuclear plants, 115 new hydro dams, 20,000 windmills, and I read your report, it's something like 400 gigawatts of solar panels, which are truly viable. Large dam projects take forever to get approved, and environmentalists seem particularly predisposed against anything nuclear. Solar panels are popular, but are they a reliable source of energy in our Canadian winters? And how feasible is it to build that many windmills? Is it possible for us to more than double our electricity output without building any more nuclear plants?
Okay, so I think the first thing to note is energy is being planned in Canada under a provincial jurisdiction. So each province is going to implement a solution that's going to fit its needs and its demographics. If we look at today's Canadian power grid, it's very vertical, meaning the lines are mostly routed north to south. That's because most of the power exchanges outside of the provinces are done with our southern neighbors. And there's much less exchange capacity installed between the provinces, and that's for economic reasons. Until there are incentives for much stronger east-west electric ties, each province is going to keep estimating its own load growth, and they'll come up with their own distinct plan for adding their generation. So based on the available sources and based on our own modeling as well, we looked at how the demand would be roughly split across Canada. The highest demand we believe will happen in Ontario, where the load will increase by about 2.4 times. And that's mainly due to electrification of the transportation and electrification of what is currently being gas heated commercial buildings. And also that's related to the fact that Ontario holds close to 40% of the country's population, right? Next would come Alberta, but in their case, it's dominated by the industrial load electrification and the heating. And on the low end, we have Quebec and Atlantic Canada, where the load would increase by about 1.25 to 1.5 times, which is still a lot. And interestingly, that was recently corroborated by Premier Legault in his opening address at the National Assembly. So this is very real. So now the answer to your question, what new power generation will be built, is that it's going to be very location dependent. Quebec, for example, has recently hinted that they're thinking of adding a lot of wind power, especially up north. In their case, the grid can afford introducing so much intermittent power because they already have a lot of stable and highly predictable hydro capacity. Ontario, on their side with OPG, they have announced recently their first small modular reactor project at the Darlington site, and some other provinces are still studying the question. Now, with all of this, it would obviously be in our country's interest to couple this with a stronger east-west power grid, because some provinces may have more potential of a certain resource that could use that could be used by their neighbors. We've seen already discussions on things like the Atlantic Loop and the Western interconnections, but these are still discussion stages. Now, you asked about the viability of all these sources. In terms of engineering a future power grid, we think that the energy mix is going to have to be led by some reliable baseload type technologies, so like hydro and nuclear. Okay, it cannot be led by intermittent sources of power. In the most practical scenario we've modeled, we did some high-level modeling. We think hydro could make up to 43% of the national power supply. Nuclear could take up as much as 25%. So talking, you mentioned nuclear. So as an example, that would mean as much as 45 small modular reactors. Or 20 larger scale can-do type reactors. Now, you mentioned the popularity of all of this. So from a project perspective, we can say in the last year especially, and with the events in Europe, we've started to see a bit of a shift in people's perceptions of these large-scale projects like hydro and nuclear. People are gradually realizing how critical energy security is, and so there's a renewed interest in building all this clean infrastructure. Now, having said that, social acceptability is extremely important, and either way, it's going to be one of the most important factors in all this decision making. And so will other things like Aboriginal consultations and environmental impact assessments. And in each case, every province is going to be making their own decisions. Now, finally, just to say, as an engineer, from my perspective, I know this is 2022. The approach to these projects has evolved a lot. We have very modern approaches today. We integrate in the project aspects like sustainability, safety, community engagement right from the start. And there is also a factor that includes that, we want the benefits to be there for the local residents, whether it's employment, economic activity, or other things.
Thanks very much, Claudio. Claudio, Rami, that's a pretty vivid description of what we're going to need to the grid to get the power we need. Where do the utility companies stand on this transition in your experience? Are they ready for such a rapid transformation? Rami study says that we'll have to build out power stations at about 3 times the rate we have over the last 40 years. Are we ready to fund and support that? Have they got a plan to move forward? How do we get where Rami says we need to go?
Well, interesting question, David. I can tell you what the situation right now is with utilities. Utilities are very mostly concerned about their needs right now, their demands right now, which are mostly house charging, because that's where the demands is right now. They are not that concerned about public infrastructure at this point. I'm talking about nowadays, looking at the next 10 years. However, this is changing. This has changed rapidly with the federal government indicating that by 2035, all our electric vehicles, all our vehicles should be electric. So that's really changing the mindset. However, this is something new for utilities. So they are not really looking into it at this point. They're mostly concerned about what is happening at homes and how you're charging your vehicles. So they are very concerned about the low voltage grid and the transformers at the end of the day, because that's where the load is right now and where the demand is right now. Now, when you're looking at the future, you also have to look at not only as Rami already said, not only at the generation side of things, which is quite significant. Also, they need to look at the issue of transmission lines and distribution lines, where the utilities are really concerned about how they're going to be providing all these loads to all these charging points. So that's one of the major concerns. And if I may have my second slide, because I wanna basically sort of give a picture of what kind of loads we're talking about and what kind of demand we're talking about. So as you can see, this is my vehicle, my charging vehicle. In my vehicle, my charging needs, and it's more or less describes what the different levels are and what the needs are. So we talk about, because we're focusing on the infrastructure, the public infrastructure, we're talking about, in my case, I would need a level 3 charger, right? If I want to charge my vehicle in about 40 minutes, or a level 2 charger, which will take several hours, depending on my needs. So I drive about 140 kilometers a day, and I will need to charge my vehicle from 10 to 80% level of charging. So I'm talking about different needs. And this is what the utilities are concerned about, particularly level 3, because that's where the problem is, in which we're dealing with this issue of, okay, I have this major significant load at a point in which I had not planned for, right? So I need to basically deliver that power, that particular feeder needs to be capable of delivering that power, that transformer, which is things that were not there before. And now the utilities are starting to realize that, oh boy, well, we need to supply this load. Not now, but in the next 10 years, probably we'll have to deal with these issues. And utilities are very concerned about how you're going to accomplish that. And one way of accomplishing this is what we're doing with utilities, is not only the issue of building infrastructure, but also managing the load, which I think is going to be necessary. The only way electric vehicles are going to be basically we are able to supply that load, at least in the next 10 years, would be by controlling the demand, by developing techniques to do that. And I think that's going to be part of the discussion, not only how much infrastructure you're going to build, but how you're going to manage, how you're going to charge these vehicles. And for that, we need to, and this is very important, we need to incentivize, or we need to a mind change from the user, from the consumer. And that's one of the major issues that we need to also think about, how we're going to educate the consumer that you're not going to just charge your vehicle whenever you need and as fully charged at all points, So the consumer needs to change their mind. And in that factor, you're going to establish this relationship with utilities in where you're going to have to be discussing this issue about demand, right? How to manage the demand. And that's one of the major challenges that's the way we're going to move forward. Otherwise, we're not going to be able to deliver what is required in the next 10 years or so.
Thank you very much. So Brian, my last question to you was how many charging points we have in Canada? But what everyone really wants to know is how many do we need to handle the EVs in the future? And how does our rollout of charging stations compare to other jurisdictions that have been more successful with their switchover, say China, California, amongst others? I believe your Canadian Vehicle Manufacturers Association has compared the ratio of EVs to public chargers in countries around the world. How do we stack up?
Sure, yeah, and if you could put up my second slide, it just shows where Canada stands right now in terms of the number of publicly accessible chargers compared to other countries. So you can see if you look at that, we're 11th. China is an obvious outlier with 1 million public chargers and growing very rapidly. I just put that up there to illustrate where we are in terms of total chargers compared to other jurisdictions. But the reality is the pure number of chargers is probably not the best metric, because what it really has to relate to is how many EVs are there on the road. And that is something that we've looked at, as have other jurisdictions. And so the most recent assessment from the federal government has a ratio by 2030 of 24 EVs to 1 charger. Compare that to a jurisdiction like California, where they're at 12 to 1. That's 12 to 1 for public accessible chargers. And if you include private but accessible to the public chargers, the ratio actually drops down even further. In Germany, they've targeted 10 to 1, and there's an EU directive for 10 to 1. So all this to say is we see more ambitious targets in other jurisdictions on this ratio. And just to give you a sense of what that means for the actual number of chargers that need to be built, if you apply the California 12 to 1 ratio to the projected ZEV fleet by 2030 in Canada, we would actually need over 1 million chargers. And the federal government's assessment is that we would need 442,000. So that's a big gap. And frankly, that's what worries me, that we have these very wide variations in what is required to support a growing fleet. And look, you can debate these ratios all day. You know, what is the right ratio? Is it 10 to 1? Is it 12 to 1? But I think what's missing right now in Canada is a very clear and well thought out plan to build this charging infrastructure and make sure that we have the electricity to support it. Our electricity system is complicated, as we've heard, and we're not seeing a coordinated effort by the federal government bringing in all the players to coalesce around a ratio that aligns with the sales targets that the government's trying to get to, and then make sure that we've got a plan in place to actually build this at the pace it's necessary. And the reason we need to do that is we have some unique Canadian conditions that you don't see in other jurisdictions. We have cold weather. We've got a massive road network, over 1 million kilometers of public 2-lane road. We have a pretty sizable rural population. 18% of Canadians live in rural Canada, which means longer drives. So these are unique challenges that you wouldn't necessarily see in a smaller European country that require some more thinking. And what we've asked is, you know, can we not have a more structured commitment to a detailed assessment of Canada's charging needs? And I'll come back to California. The California Energy Commission does a biennial assessment of their charging infrastructure needs to tie it to what the state wants to achieve in terms of ZEV adoption. And if you look at the reports that they put out, I recommend anyone, if you haven't had a look, This is comprehensive. We're talking hundreds of pages of analysis where they're going, right into almost the zip code to try and figure out what's needed, where are the underserved communities, and how do we make sure we have this infrastructure in place. And that's missing right now in Canada. So, if there's a call to action coming from this, it's please, let's get a plan together. Let's get all the players in the room. This is solvable. We can overcome these challenges, but we've got to be more focused.
It strikes me that if we're comparing ourselves to California, we need more. As you mentioned, it's larger and it's colder and larger here in Canada. Plus, we have in roughly the same number of cars in our country as they do in the States. So it strikes me that we'll need more, not less, chargers than they do in California. Thanks very much. Talis, now besides the benefit of the fact that your magic roads would seem to completely eliminate range anxiety, I believe your organization also says that these electrified highways can also save us a boatload of money. I can only imagine that rebuilding our entire highway system with an electric grid underneath would be quite expensive. So how do you save all we taxpayers money? Can you walk us through that calculation, please?
Certainly, and as we talk about the electrified roadways and the differences in that, I think one of the keys is to keep in mind that we're not going to electrify every roadway, right? And I'll get into that a little bit more later, but I forgot to mention up front that Aspire is a National Science Foundation engineering research center in the US. We're across 9 different universities. We have over 300 faculty, students, and staff across that, partnered with 4 of our national laboratories, and have over 60 industry, government, and nonprofit members. So when we look across that group, we're tapping into lots of different people with expertise. So if you could bring up my first slide, please. Some of these numbers were done looking at the techno-economic analysis of this. So if you look at kind of an estimated cost for what does it take to drive a gas or diesel car today, 16 cents a mile. These would be US dollars, not Canadian. The cost of an electric vehicle is really dominated by the battery. The electric vehicle is much simpler when you remove the gas engine and all of the other pieces associated with that, but the battery dominates the cost. So if you want a long range battery, and as you look at most of the vehicles and where they're going, you're seeing moving from what was 200 miles to now 300 miles and looking at 400. You had Tesla just deliver their first electric semis with 500-mile range on those. The batteries are getting bigger, and that just drives the cost up. When you add in ultra fast charging, the cost to build that charging is expensive. So if we can put in an electric road system, you can actually decrease the cost of transportation for anyone. And when you start looking at how do we do this, we're going to do the main roadways. One of the keys that's going to be somewhat different in Canada, which is going to be similar to some of our Western states in the US, is that for people in rural areas, you are going to need a longer battery than somebody, longer range battery than somebody who lives in a major metropolitan area. So if you live in Toronto and you're driving more locally, that's going to be different than if you're living in BC or Alberta, and you have much longer commutes. But if you can charge in the main roadways, that really changes the game, and it changes it significantly for people that live in multifamily housing. How do you charge if you live in an apartment building? Where's that charging end up being? So the cost really depends on, can you shrink that battery? If I don't need a 500-mile battery and I can get by with a 100-mile battery, that dramatically changes the cost equation. And you put money into the infrastructure rather than in buying, trillions of dollars worth of batteries.
So I think what you're saying is the cost of building the roadways, even with these inductive charging networks under them, across, say, in your case, the United States, across Canada, is actually less, I believe, than the cost of equipping electric vehicles with huge batteries. I mean, 100 kilowatt hours in a Tesla could now become 50, and the savings there is actually pays for the roadways to be installed. Is that about correct?
Absolutely. You're changing the model. So in the US, if we said all vehicles needed a 500-mile battery, then you're looking at $7.8 trillion for that cost of all of those batteries. But we can electrify the interstate highways and the major roadways in the US for about $30 billion a year. So now you switch to a public-private partnership model. You get things like the Canadian pension plan that has billions of dollars they want to invest for long-term sustainable, returns. They invest some of the money in building out the highways, and they're paid back by some of the money that we're paying. Rather than paying at the pump as we gas up, we're paying as we drive over these roadways. So we changed the model, and in the US, our roadways in most states are not in very good condition because we're relying on a gas tax that hasn't been raised. So we don't have the money coming back into the states to pay for good roadways. And if we change this, we can actually have better roads to drive on, and we can make it cheaper for everybody to drive.
Well, that's a pretty darn good combination. Better roads and cheap. I like it. Rami, we just ran a story about a study by an American utility company called National Grid that estimates that a regular service station will require 5 megawatts of power by 2030. That's equivalent to like a major sports stadium. By 2035, a truck stop will need a 20 megawatt capacity, equivalent to what a small town of 75,000 needs. That's not cumulative for all service stations, that's for each one. How does the grid manage that? Does that kind of usage require a change to the type of transmission system that feeds the service stations? Walk us through what's involved and how quickly do we need to get there?
Okay. So I spoke earlier of the challenge of adding the new generation. What you're raising now is the other big challenge, which is reinforcing the transmission and distribution systems to get the electricity where the load is. Now, the first thing is it needs to be very, very reliable if our entire transportation sector is going to depend on electricity. And it needs to be able to withstand the more and more extreme weather events that we've been seeing across the country. For information, typically the criterion for designing these things is what we call N-1, meaning you can lose any one element and the grid still works. Is that going to be enough if we're going to be that dependent on electricity, or will we need something more severe? Now, we won't succeed in supporting all these large charging stations or electrify in general unless we combine the new generation we've been talking about with other initiatives. One of them is energy efficiency measures, meaning changing the consumption profile from the user end. And I believe it was Claudio who mentioned this very eloquently earlier. We're also going to have to implement what we call DERs, or distributed energy resources. This is already widely available in some places in Europe. What it means is we're going to allow single homes or neighborhoods or those charging facilities like the one you were referring to produce their own electricity as well, whether via renewables together with energy storage or via new technologies like small modular reactors or others. And thus we reduce a little bit the reliance on the grid, and we reduce the load on the grid and the need for that equivalent amount of generation. Now, finally, and most importantly, we going to need to digitize all of this. We need to make sure that we have smart algorithms that are going to be able to forecast and to plan the distribution of electricity in an optimal way, to take into account that now we have to charge all the EVs. And so these smart algorithms can also work with commercial systems and with your home systems to manage how people's electrical consumption at peak load should be, what should go to heating, what should go to your EV, etc. So as you can see, there is a lot to develop, and there isn't a lot of time. So the other part of your question you mentioned in terms of being ready on time. So it was mentioned a bit earlier, we consider that a new installation, like say a new hydro dam or a new nuclear plant, from the initial discussions to completion can take up to 10 years, say like 8 to 12 years roughly. So we're going to need a major paradigm shift in the whole system, including the government, to see how we get those timelines down. We're going to have to see how we can streamline the approvals, the regulatory processes, without necessarily skipping them, just to see how they can still fulfill their purposes, but in a much more efficient way.
Thanks very much. Claudio, so Rami just discussed the loads imposed on the grid by major truck stops. Those trucks are going to also pose a huge problem for the charging points, aren't they? Serious long-haul trucks will need batteries of between 500 and 1,000 kilowatt hours, 5 to 10 times larger than the most powerful Tesla Model S. My back of the napkin calculation says at the top of rate charging now available, a long-haul 18-wheeler is going to need more than 5 hours to recharge at a 350 kilowatt charging station. So what's the solution? Even faster chargers? How big can we go? And if we can go bigger, is that technology transposable down to cars?
Good question. Is a very vexing question. How are we going to deal with all these charging load, especially for big trucks? How are we going to accomplish this? Rami addressed quite a few issues that I believe are going in that direction, like local generation, solar panels, local wind turbines, small modular reactors, etc., that will supply that load. However, on the other side, you have to charge these vehicles, right? So there are various solutions being looked at. One is, change the technology of the battery, right? So there are solid-state batteries being discussed and maybe commercialized soon, which are going to have faster charging rates, less weight. So that's going to change the equation here, or address that issue. Fasting charger stations as well. So that's going to help in that regard. But another totally different track that is happening in Europe and North America is looking at this as well. Is, do we really need to have trucks fuel of heavy transportation, long-haul transportation fueled by electricity? Can we do it with hydrogen? And for example, Germany is looking at this very carefully. Fraunhofer Institute has a lot of research being done in this area of, for heavy transportation, maybe we should be looking at hydrogen instead of electricity. So this is all different options that are being discussed, analyze and to try to address this particular issue of how we're gonna deal with heavy transportation.
It certainly seems like we have a challenge if we're going to make all the vehicles on the road green. Thanks very much. So Brian, one of the most frequent complaints I hear about EVs is the wonky way we get billed for recharging. Currently, it's basically a time-dependent charge rather than how much energy you've taken in. It seems patently unfair and an archaic leftover from the home grid system. Are we going to ever get a use-based system, and how soon? And when are we going to be able to pay for our electricity with a credit card like we can at a gas station?
Excellent. Yeah, and just a quick comment on the previous point around the heavy-duty charging. If you combine heavy-duty with light-duty charging requirements, particularly in a fast charging environment, so imagine an en route on the highway, and you look at a typical gas station, 12 pumps, you get 500 kilometers of range in 5 minutes, and you apply that to what would be necessary for DC fast charging to have the same throughput. There's some good estimates out of the United States. You're talking about 30 megawatts of power at one of these facilities, which is the equivalent to what you see in a small town. So huge electricity requirements for a gas station at a major thoroughfare where you've got heavy and light duty vehicles charging quickly. But to your question, when it comes to the way that we are charged, this is a big challenge. It is time-based, as you noted, which is a problem first from the business model perspective. It's hard to make the case as a business owner to install a charger at great cost. I mean, we've heard some of the estimates of what it costs to put in a fast charger at your business if you're charging on a time-based model. The good news is we are seeing some progress here. Measurement Canada has been developing requirements for EV charging based on the amount of energy consumed. So that's good, and they've started to accept applications for level 1 and 2 chargers that would allow billing customers by kilowatt hour, but they haven't done it yet for level 3, which is going to be important because that will be a key type of charging going forward. So I'm hoping that we'll see more progress on that next year, but that absolutely has to happen, and it has to happen quickly to make this more convenient for consumers and to make, I showed you that gap between government funded charging infrastructure and what the government believes will be private sector. That is a huge gap. And the way that a private sector operator can charge is going to be really important in making these facilities profitable as the fleet increases. One other thing related to this, and it's to your last point around, can we pay for a charge with a credit card like you do at a gas station? What this comes down to really is convenience. We need these stations to be as convenient as what you do when you go to a gas station right now. So you have to, first of all, be ensured that it's reliable. Will the charging station work? We've seen all sorts of data coming out about charger downtime, and there is no regulatory environment in Canada right now to mandate charger operability, and that's a problem. If you look at the most recent J.D. Power survey of consumers' experiences at charging, this is out of US data, 20% go to chargers and don't even charge. And the reason? It's not working. So that's a big problem. So we've got to make these stations more convenient. They have to have higher uptime, and we have to ensure that you can pay through a simple method like tapping your card and not have to, currently I've got about 4 different apps on my phone for charging stations. That is not convenient for most Canadians. So there's a lot of work to do here on the convenience and payment side of things. Thanks
very much, Brian. Talis, I mean, your inductive roadway would seem the ultimate in convenience. You just drive. The big question, though, is how reliable would this new road network be? After all, governments, yours and ours, are notoriously bad at road maintenance. What happens if there's an electrical failure beneath the road surface? Does it take out the entire charging grid like a blackout in a city? Or can you localize the failure so that everyone can keep EVing along?
So I appreciate that question. Love to answer that, and I'd love to reply on some of the other questions that have been discussed in this. So the way we will build the system out will be like the new Christmas tree lights and not the old ones. So in the old, Christmas tree lights, you had one bulb that went out and it took the whole string out. And then you had to try to find out where the bad bulb was. Thankfully, people figured out, okay, we're gonna build these a little bit differently. One bulb goes out, it only takes out that bulb. We would build the system in the same way. So if you lose a section of the roadway, it only takes out a small piece, you can still use it. And one thing I should mention is that we can build the power levels into this. So we only need to electrify 1/3 to 1/4 of the roadway. So you don't have to electrify every mile. You pick the right sections where you can do it most economically, and you can conduct enough energy into the vehicle that it can allow them to drive not just over the section of roadway that they are, but for the next, say, 3 sections, and recharge the battery up as well, because this only works, and I'll talk about heavy duty in a minute, if you can charge the batteries up fully when the vehicles are driving on the roadway for a certain length of time, then they can get off and they can drive out off the roadways and then come back and recharge on the roadways. And the model that we're using for that is more heavy duty vehicles. But I do want to reply to a couple things. From the charging power point of view, it is really important for a DC fast charging for big rigs to be able to charge them fast. So we have a 1 megawatt stationary wireless charging pilot that we're doing with UPS and Kenworth in the Port of Seattle, Port of Portland. So during the 340-mile round trip, which is over 500 kilometers, the battery isn't big enough to do all of that, but there's a mandatory half-hour lunch break that the driver will pull over the wireless charging in their truck, take the half hour, eat their lunch, will be able to get enough charge in that half an hour to do the full round trip with a smaller battery. But for DC fast charging for long haul semis, you're going to need 1.5 to 2 megawatt DC fast chargers for that. And that's a huge load on the grid to think about plugging that in. And it's going to, if you're not doing it wirelessly, you're going to have a massive liquid cooled cable that people will have to plug in. if we come back into the question of building these stations, there are some interesting business models that are done. So Watt EV is a startup in California that's building a new station out in Bakersfield, kind of out in the Central Valley. And they are actually buying vehicles that they will lease to companies. So they're going to take it, they're going to take care of the charging infrastructure. But in Bakersfield, they're building a nice big battery backup where during the night they can actually bring in power where it's much cheaper and have that to cut down on the demands of the infrastructure. So if you think about plugging in a 1 megawatt truck, there's a huge spike that you need. But if you can pull that locally from the battery, then your grid infrastructure needs. So they'll be able to actually charge vehicles using more power than they actually have for the distribution into their truck stops. So there's some interesting things that companies are doing as they're looking at ways to do this. With respect to the time-based charging, in the US, that varies on a state-by-state basis. So certain states, only the electric utilities can charge per kilowatt hour. And so there are about a dozen states left that are still on that. And it makes absolutely no sense because as you charge a battery, you can put a lot more energy in when the battery's low than when it tops up. So if you think about filling a battery is like pouring a beer into a mug. If I have exactly the mug that can take that amount of beer, I can't just dump it in because it's going to foam over and I'm going to lose a lot of the beer. You have to pour it slowly as you get to the top. Filling an EV battery is the same way. So if you're paying by time, you're getting much more energy in when you start to fill than at the end. It makes absolutely no sense. And we have to get our state by state, to change those as we go in. And then the paying by credit card piece. As I drive my Tesla, the Tesla knows my car. It knows I have a payment. When I pull into a supercharging station, I get out, I plug it in, it starts charging, I finish, I unplug it, and I leave. I'm not tapping a card at all. That's ultimately where we have to be in our system. In the US, 4 apps is a small number, Brian. I've got probably 5, 6, and I don't have all of them because I'm using the Tesla stations most of the time. Those have to go away where you have agreements between all of those and have the intelligence built in so it recognizes your car and you're able to actually do that. And that's what the system will have to build behind the scenes for the electrified roadways as well. So if you could bring up the slide that I have on the importance of long-haul trucking in the US, this is where we're spending a lot of our time from an Aspire point of view. Because are there challenges in light duty? Do we need a lot more charges? Absolutely. But when you look at how we get our freight across the US, and Canada moves a lot more freight by rail than we do in the US, but 70% of our freight is transported via truck. And half of that travels over 250 miles, 30% over 500 miles. So that long haul trucking, when you look at the amount of greenhouse gases that are behind that, we have to find a solution. So if we were to electrify just the interstate highways, that's only 2.5% of the US roadway lane miles, that accounts for 50% of the truck traffic, right? We can look to hydrogen, as was mentioned, but we have a fundamental challenge with hydrogen because if you start with 100 kilowatt hours of renewable energy, to use green hydrogen, you need energy to create the hydrogen, then you have to store it, and then you have to convert it back to electricity to then use to power the vehicle. And you end up with about 23 kilowatt hours of that energy used to power the vehicle. If you're doing battery electric, you don't have to create the hydrogen, turn it back. You end up with about 69 kilowatt hours of renewable energy powering that vehicle. If you're on an electrified roadway, you're at 77. So it takes 3 times the amount of energy for a long haul truck to be powered by hydrogen than by battery electric. Now, if I'm an electric utility company and I'm being paid to build out resources, that could be a great thing. But the problem is the amount of renewable energy that we will have to create. If you think about all the energy we're using and moving our vehicles across, think about creating 3 times the amount of energy that Rami has already been talking about if we're going to use hydrogen for powering our vehicles. Hydrogen is going to be really important for certain market segments. If I'm doing open pit mining with massive vehicles, I'm going to want hydrogen. If I'm building a steel plant and I need that hydrogen as part of it, I'm going to need hydrogen. But for long haul trucking, producing 3 times the amount of energy to make that happen is going to be a real challenge.
Okay. Well, guys, I had meant to get to some reader questions, but you guys have been already so edifying. That's all the time we have today. First thing I got to do is thank Talis, Rami, Claudio, and Brian for joining us. Gentlemen, I think our readers learned a heck of a lot today. I know I certainly did, and I thank you for it. I also wanted to send a special thanks to everyone who joined us for this crucial discussion, and especially those who wrote in such insightful questions. Anyone whose question was not answered, and that was nobody, please look to this Friday's Motor Mouth, where I will be getting to as many of them as I can. And this ends this season's Driving into the Future panels. For all the panelists who managed to make complicated discussions a little more accessible, my many thanks. For all those who listened in, my hope is that you have a little more insight into what our automotive future looks like. Thank you all for joining us today.